Okay. All right, I got my pencil today, so I should be a little easier to read. Okay, so the request last time was for some filters. So here is a filter example. Given the graph, what type of filter is this? Okay, so I'm hearing a consensus bandpass. Why do you say you think it's bandpass?
Wait, no, it's not high pass.
I mean, sorry. So I've heard two, high pass, bandpass. So how do you determine which one it is? It looks like both, right? It's the form, looks like both. Yes,
We
Adam?
can look at the magnitude there, and it steadies out at 0 decibels for the high frequencies, which would be a passing. So it's a high pass filter that just happens to be that spike right there based due to how it's constructed.
I'm going to refute that. On one of the homeworks, or on the quiz we had last week, I had one that looked like that looked like a low pass, and then it went into a band pass, or a band reject. So even though it had it went down and then it spiked down, so I believe it's a band pass.
Is the fact that it's
Even though it does flatten out at 0 after, because that's what it did on the other one too.
So if it equals 0 dB or higher, either before or after is what you're looking at. If it's bandpass, it's going to be below 0 dB both times. High pass will be one of those times. So you can argue that it's actually both, depending on your application. It could actually be used as a bandpass for what frequency? So that would be your omega naught resonant frequency. So you would say 1,000 radians per second. I had to look at what units was on this one. So you could argue that it's actually a bandpass, but it is because of what you're looking at with that 0 dB level being before or after. Before, it's not, so that means it's either going to be a bandpass or high pass. And because it's at 0-ish dB, after, it's actually a high pass. If it went below that after, it would for sure be a band pass. But you could argue, Bri, that it is a band pass too. Yes?
How is it a high pass if the dB is 0, like when it's passing?
So 0 dB converted to a volt per volt is 1 volt per volt.
Okay.
And so that means that whatever you put in, it actually comes right back out. So you're multiplying it by that 1. So because it's dB, it gets confusing.
It's still like being passed.
But 1, yeah, because it's 1. Once you hit a negative dB, you know that it's actually less than 1 and it's attenuating, or what's called attenuating the signal instead. And then that way, that is not considered passing, it's rejecting. Okay. All right. So does that make sense of what you're looking for is that 0 dB comparison to determine whether it's high pass or band pass in this case? So I would say it is high pass. Omega naught is 1,000. Does this have a high or a low Q? High Q, correct. So the Q is really sharp and has a really sharp peak. So you would say it's a high Q.
So then is all the stuff on the right, is that also part of the pass band because it's a high pass?
So you would say at 1,000 radians per second, anything higher than that, you're passing.
Okay.
Anything below that, you're not. It's less, it's going to be like, if I put in 5 volts, I'm going to get out 0.1 volt. So it's not passing it. Yes, Marley?
Does the pass band start where it like initially reaches 0 dB or at the resonant frequency?
At the resonant, well,
Cause like, isn't it also typically passing like in that gap? there?
yeah, so you would say at minus 3 dB. So minus 3 dB would actually be what you would consider the omega C.
Okay. Okay,
And then, yes, it passes everything after that.
gotcha.
So yes, you do go down, so it's gonna be, what-ish? You go in there. It looks like about
It's like 500.
1, 2, 3 in.
Cause it's.
So
You can count.
it looks kind of about that 3 in, so that would be 100, 200, 300, 400, 500, 600, about 700 radians per second. But it's kind of hard to read that interpolating it off the graph. So if I just saw this graph like on a data sheet, I would be like around 1K or 1 radians per second or higher I would want to use. And that would be a safe location to say like, okay, it's definitely going to work after that. All right, so if I asked you this question on an exam coming up, I would be asking you for the high pass. Is it a high or low Q? And what is the resonant frequency? Because it's hard to interpolate off that exact value, unless I marked them. And then I could ask you there. All right, any other questions on this? Okay, looking at this one. Okay, here, low pass. Any other thoughts?
It's got a high Q value because we can see it, or maybe kind of a mid Q. We can see it drop about 40 decibels in a decade. So it's not super high, but it's got 2 poles.
Okay.
I was gonna say that it had a low Q because it looks like it spreads out a lot more.
Definitely
This
medium
graph
at
is also
least.
zoomed in a lot.
Medium at the
further.
least, yeah.
So a low Q would barely go up.
Okay.
So this would be like a medium or high Q if it's a low pass.
Gotcha.
If you thought that this was a band pass, then you would be like, okay, well, if the band pass is right here, that's at 20 dB, so then my 2 points there, this still would be a high medium Q, because those are my 3 dB down, so it's 17 ish dB. Does that make sense?
On the test, if we say like this one's a band pass, is that gonna?
You would be marked off.
Okay.
Why? Why is it not a band pass?
It's passing at the beginning right before it's like.
Correct. So it's passing here.
Okay.
So even though the form of it goes up and down, it's actually a low pass filter with a high Q. And then after it, you can see that this is not passing. Yes, Bobby.
On the exam, will it be obvious if the Q is higher or lower, or will it be something like this, which would be easier?
This could be an example. This is one I've used in the past. I'm only going to ask you high or low. So you don't need to worry about the medium. And hopefully you can see there, like, yeah, that does have a high Q to it. It's got a really big peak. Okay, this one. Okay. So here you can see, yes, it's passing. And this is at 0 dB, so it's passing.
Band reject.
What? But how is it passing later?
Because
It's
as
at
I
zero.
researched it just says no to one specific.
Oh, yeah, done. Okay, yeah. Okay.
So band reject.
I knew that at one point.
Okay. Yes, Adam?
We can infer it's got a very, very high Q with that band reject, because it's rejecting like negative 250 decibels there.
Yes. high Q.
This diagram really is about like 10K per second.
Okay, and then omega naught is at 10K, correct? 10K radians per second. Okay. Okay, good. Think everybody got that one? All right. What about this one? I don't have it labeled, so that will be our omega naught, whatever value that is.
Band rejects.
Okay, correct. Okay, so 0 dB, 0 dB, so band reject, high or low Q?
I give that one I guess it's pretty zoomed in. I'd say that's a high Q.
Okay.
What's the x-axis on it?
Yeah, how do you,
Because if we look at the minus
Oh, yeah.
3, it's only like it's.
but it's just one mark, so like
Two
17,
decades, so-
minus 17 dB is where you're looking at.
Uh-huh.
And so you can see that intersection is really close together when you're like, oh, it's only, between, like really close in there. Yeah. So this would be considered a high Q. What would a low Q look like?
The band that rejects would be really long.
Okay. So what, like maybe, so this would be a low Q. A lot of times they'll have more of a flattened region down there instead of a spike. So it will look more like that, kind of a curvature of that. Or it's just really spread out and could be, do a different color. Like, now that didn't work too well. Let's see. Yeah, there we go.
Why would it be flat at the bottom? Like
Okay.
green line?
Just what's creating so that your poles and zeros are creating that steepness of how steep you're going down. And then there's going to be a pole location, typically will be one on each side. And then sometimes for the higher Q, you only have, like, it's really close together of those two pole locations. And then there'll be a pole and a zero to make it go back up. So you have two going up, and then there'll have been one that creates it going down.
So.
Or two zeros that make it go up.
So if we were looking at that green graph, we assume that it has lots of poles and zeros because it goes really steep and then it goes flat and then it goes really steep and then flat again.
Uh-huh. Well, it wouldn't be a lot, but it would be that the values of them would be spread apart. So going down has been a pole that's created that. So your pole starts way over, somewhere over here.
Two or three poles, for example, in that one location make it so steep, or
Yeah, so the steeper it's going to have, it could be like one pole with cubed or something where it's, it goes down by 20, 40, 60, yeah. So it goes down really steep at that one location, or it could be several where it's like, okay, at this first location, and then there's another pole here, and then another pole here, and then I have the steepness of it. So it's like a little bit, let's see, 20 dB, then it goes 40 dB, and then it goes 60 dB, and then it flattens out, and then the zeros cause them to go up. So those with 2280, that might have made more sense. Those that not, then you will understand that after taking 2280. Okay, so does that make sense with the green and the purple would be low Qs? Okay, what about this one for the purple one on the top?
Low
Okay, so first off, band pass I heard.
Band pass.
Everybody agreeing that this is band pass? Okay, correct. It is band pass. And that is because you're looking at this 0 dB level. And all of these go below 0 dB on the before it and after it. So that is going to be band pass. Okay, the purple one. Well, first off, omega naught. What's your omega naught here too?
It's gonna be 10.
10 radians per second, correct. Okay, the purple one, that one is going to be a low Q. The red one, high Q. Okay,
The low Q is kind of cut off on the screen. Just the tad bit.
there we go. All right, so minus 3 dB is kind of this, oops, green maybe. So that level is where you're looking at the points.
Wait, why did you do the minus 3B from the?
Oh, sorry, nope, you're right. It doesn't have a value there. So it would be 3 dB off of this value, so it's going to actually be up here somewhere. Sorry. Yeah. All right, so those middle ones is kind of more questionable, like whether they're high or Q or low. So
Would you say the blue one is high still?
blue one, I would probably lean more on a higher side. But that's about the point where it starts to get questionable.
But like high versus low. you're
Yeah.
going high.
Yeah, I would go high for the first two, and then the others, I'd probably say they were low. Okay, this one. What do you think?
High pass.
Okay,
It's too easy.
correct. High pass. Before it, you're seeing that it does go below the 0, and then after it is above the 0. So this is for sure a high pass. Would you say this is a low Q or a high Q?
I'd say it's low to low Q.
That frequency range, if you look at the numbers, is not that much. That's like a frequency range of maybe 100 hertz.
Can't keep
On that
changing
spike
the
there.
schedules on me. It's throwing me off.
But it only goes up 10 decibels, so.
Yeah, so 10 over 100, that's like,
So this is like 8, so this is going to be, this is dB. I forgot to put that on there. So actually, I think that line is 10 dB, and no, I think it is 8. 8, so 5-ish is going to look like somewhere in here. So it would be these two right there.
so it's about 50 frequency.
So medium Q.
Medium Q. Okay, I'll make mine more obvious. We'll say this is a medium Q.
Why wouldn't this be a high Q?
I would lean towards high Q if I was going to make high or low. Low again for a low and a high pass makes it look exactly the same. So it would be more, this would be considered really the lower. A low Q for a high and a high pass and a low pass. It's very smooth. So I would lean towards saying this is a high Q. What is your resonant frequency? How much? 200 hertz. And what would you say is your mega C here?
About 100, because our passband gain looks like it's about 3, and 100's about at the 0, so I'd say it's about 3 lower than our passband gain.
Correct. So you look at, once this has gotten to be more of a steady state, which is about 3 dB, and so 0 mark would be right there. So it does look like about 100 radians per second. So that would be where you would say the corner frequencies.
1 over radians per second.
Oh, sorry, I meant to put hertz. Yes, no, hertz is is 2 pi f. So to get radians per second, I would multiply that by 2 pi. Okay, any questions on this one? Okay, this one, the red one.
Low pass, high Q. What's on the bottom?
Okay, so low pass, I'm hearing some agreement on low pass. Everybody seeing the low pass? Okay, again, about at 0 dB, and then it's below 0 dB after. High Q, as you can see, these two are going to be low Qs that are very smooth. Those would be considered the low Qs. So it does have a high Q. What is my omega naught?
2K.
Correct. So remember the lines in here for a semi-log. The first line is 2K, the second is 3, 4, 5, 6, 7, 8, 9. I didn't mark those very well. 10. Okay. So each line in there goes up by a value of 1 in whatever the unit is. So in Ks, so it goes 1K, 2K, 3K, 4K, 5K, 6K, 7K, 8K, 9K, and then 10K. And then over here, this becomes 20K, 30K, etc. So this would be 2K. And again, this is in hertz for omega naught. And where's my omega C? Again, this is hard to read. So I'm going to make a guess. Again, I will make these much clearer if I do ask this question. So this is about minus 3 dB. So that looks about to this, it's about 3. So there. What one will that one be?
3K.
I think it's 4K. Two marks. I know. That, as I said, I'll make this more obvious, but 4K hertz. There's a little line in here. There's another line in here. Okay. Okay, questions on this one? Okay, I think those are all that I have. Okay, so let's do, find, no, I don't have these. So let, f of omega wait, sorry. Let me try this again. I was like mixing the time domains. Okay, 8 plus, A minus J omega 4 omega. Plus 7 over plus J omega. Okay. Find f f of t. So take a minute to solve for this one. And then after you've found the equation, find at t equals t equals 5 seconds. And you can leave the, let me go back to this one. Well, yeah, find it at 5 seconds. You can leave the E, like you don't have to multiply out the E. You can leave that answer with the E in it. Three, two.
I think the two we use 4. Cause that is a J. So E negative J4.
Okay.
And the thing, it's E to the negative J negative T.
Oh, yeah. Oh, yeah. Okay, I like that idea.
Okay, so what did you guys get?
8 delta T plus 1 delta T minus 4 plus 7 E to the negative 4 T to the negative 4 T U of T.
Okay. And then at 5 seconds.
It's just gonna be 7 times e to the negative 20t, or e to the negative 20.
Okay, so first component, the delta t is 0, right? Because we're not at 0. And then the one that's shifted at 4 is going to be 0 also. So then it's, yeah, 7e to the minus 20, whatever that value is.
The delta T goes to 0
Mm-hmm.
whenever it's not at 0.
Correct. So this looks like, if I was to graph it, at 0, I have a spike of what we consider magnitude 8. And then at 4, I also have a spike of 1. And then after 0, I have that 7. So it's added. So I've kind of have this shift, and then it spikes, and then it goes flat. So that's kind of what that graph looks like. So it just adds on a value at 4 of 1 to it.
What would be a value at?
Sorry, it would be below the 8 if you start at 7.
How did you get the 4 for T0?
Yeah, wouldn't it be at 1? Or, I guess, no, never mind, it would be.
Because it's T minus.
Minus 4, so that
So
just
that is
spikes it.
How
It
did
makes
you
it
know,
four.
how did you get that, the 4 up in the equation?
It's e to the negative j.
Oh, is that a 4 up there?
Yeah,
Oh. Okay.
that is a 4 omega. Okay, any other questions? Okay, what would it be at t equals 4 seconds?
The
Are you
8
multiplying
is
it by
the,
8?
no, the 8 is times just delta t. The delta t minus 4 is the one that gives us a value of 4. So it's 1 plus 4.
So this has a unit of 1 in front of it.
T equals 4.
Would it be
So-
e to the negative 16?
Yeah. 4 times 4 would be negative 16. There we go.
Wait a second. The delta t, the first delta t would be delta of 4, because t is 4. So, didn't we just point out that at 4, the graph is up to 1?
That's the.
Yeah. So
Right, duh, okay. Yep.
you got it? So this value is 1 at 4. And then this is the value at 4 for that portion. And then this one, because it's at 0, will be 0 at 4. So at t equals 0 seconds, what do we have?
8.
0 plus 7.
Is it
Ooh.
So that becomes
1.
1, right? E to the 0 is 1.
No, but
this
the
u of t makes it so that it's 0.
Oh, u of t actually is defined at 0 of the value 1.
Oh,
The negative 1.
Uh-huh.
Okay.
Yeah. So it's defined at 0, but the sign of t is not defined at 0.
That's what I'm saying.
This is nice, we could have a question like this.
So the sign of t that goes negative 1 to 1 does not have a definition at 0. You interpolate it usually as 0. So you say it's 0 at 0 for sign of t, but for u of t, it is the value of 1
Okay.
at 0. So that one is defined at 0. Okay. Other questions? You guys good with this? Okay. So let's run through, I think we have time. Let's solve this one for IL of t. Let me find what these values were. Okay, so IS of t is defined as 6 amps for t less than or equal to 0, and 6e to the minus 2t amps for t greater than or equal to 0. And then R1 is 10 ohms. This is 5 ohms. L is 0.6196 henries, and C is 0.1076 farads. And we want to solve for IL of t using Fourier transforms. So go ahead and write equation set to solve for this. Oops.
I said for I out, we just want this voltage over R. Yeah. Right. And so I was just gonna do no analysis for this, but after I looked it up,
Here's a hint. Taking the Thevenin will leave you with just one node instead of two. You can still do it with two, but you have to have, you have another set of, you have another equation set, so you would have to use a matrix to solve. So I think it's easier to find the Thevenin, which is really easy there because you disconnect it from the circuit and you just have the current source and the resistor.
Is there a reason you left it in S instead of moving it to JW?
It's easier to see for me. So I like to put in the S and then just change it to J omega before I transform it back. But if you like to see it in J omega, I just don't like looking at the J omega. S looks easier for me.
I don't care, I was just trying to separate it from the class in my brain, so I'm like.
Yeah.
So let's do that. If you can move it to
Can you combine your 10?
I'm just thinking this is 10 plus. Or you can
Right,
say
but. Yeah, yep,
it is an option.
yeah.
I'm just so transfer this 3 times.
No promise anything, check your works.
I just do it, correct?
Always, I know, you're so cool.
All right, so IS changes to what?
Is it 6 plus, well, like the original equation is basically like 6 plus 6, wait, hold on.
How do you deal with the fact that?
Cause it's, I feel like you're gonna have like a U of t.
It's, the original equation is gonna be 6 plus 6 e to the negative 2t u of t minus 6 u of t.
So you said 6 what? U?
6
Six.
plus.
6
6
plus
plus
6e to the negative 2t
U of t.
u of t minus 6 u of t. Or 6.
Well, but we have a U of
Does
t.
that work? 6 minus 6 u of t.
Yeah.
That gives you 0 for that portion. And then a 6e to the minus t u of t.
Okay, wait, why do we have 6 plus?
So,
The
let's
6 is
look when
before
it's
the 0.
So when it's before the 0, we want it to be 6.
Okay.
And then after the 0, we want it to just be the 6e stuff. So if we so we need to get rid of our previous 6.
Yes, yes, okay.
So we turn off this one.
Okay, so changing this to from the time domain becomes what?
12 pi delta omega.
Yeah, I'll just write 12 pi.
Plus
Minus what?
6.
Yeah, minus 6. And then what does the u of t become? Or u e, whatever. Plus,
1 over, or I guess 6 over, 6 over 2 plus j omega.
correct. So these two combine, so you end up with 6 pi delta omega minus 6 j omega plus 6 2 plus j omega. So that is going to be my I of s.
Where did the 6 u of t come from?
The minus 6 u of t? So this is only 6 until you hit 0, and then it goes away. So in order to get that away, you're subtracting off 6 u of t. And that will put a 0 there.
That's how we do it.
Yeah. Okay. Let me get back to where the math was on this. Okay. Copy. Okay, so this is going to be similar to how it was with this except that you have, instead of 60, 60. Did I forget a 10? Oh, the 10's there. Yeah. So then you have, the only difference is this last portion of the 6 pi delta omega. And when you take, so you have to worry about that one with the transform. But you will end up with the same answer. You have A. So if you want to change it to S's is what I mean. You can change it back to S's and then work with the equations with them in S. And then you can change them back.
Does
And-
that mess up your like J multiples?
No, it ends up being the same. Let's see. Here, let me copy this and then copy. So, paste. Okay. So here I would change to IS. I would just use, so delta omega you have to keep the same, but you can just treat this as minus 6 S6 2 plus S. And so this ends up being, I don't have this one in Wolfram, but you can use Wolfram to end up getting your N numbers. We don't have time today, but I'll do this math and then I'll post this so you guys can have this to work through too. All right, any questions about the steps that we just went through for this? Okay, so they're the same steps except for we don't have to find the initial conditions like we used to for the Laplace. Instead, for the Laplace, we just transform them. So one, we may have to manipulate the mathematical expression of our input to get something like this. But then from there, you would treat it just the same, write your expression. And again, you can keep them in S, and then at the end, you can swap them back to j omega and then transform them.
Will we have a question with varying time source like this on the exam?
No. So for the exam, you're going to see, I would give you probably an easier expression to transform, and then I'm going to break it up to give you, so you wouldn't have to change this back to the time domain. I would let you, like, if you were going to work through this, do that in homework, and then I'm going to ask you more of what I did, like this kind of a question, to just transform that expression. But in this one, you would maybe have to manipulate it. Well, you do. You have to manipulate it with the partial fraction expansion. So I could still ask you to do that partial fraction expansion. So make sure to review that before the exam, but mainly focus on being able to write this expression. So being able to transform it into the Laplace domain from the time domain, and then being able to write an expression for Vx and know how to solve this using whatever tools, calculator you use. Does that answer your question, Bri? Okay. All right. See you guys on Monday. Remember to do, if you haven't done the quiz, it's a max power transfer quiz. It's due by tonight. So make sure you do review that one, or do take that exam or that quiz, and then prepare for your exam on Monday with your group work or individual work. Okay. See you guys in the lab on Monday.
I have only worked on my first